Our first speaker for this session is going to be Nicholas Seeger, who will be talking about subcube quasi-randomness for Boolean functions.
And thank you. Thank you for the introduction.
Sure.
And also, and thank you to everyone for coming, and also to the organizers for hosting this wonderful conference. And so, what I'd like to talk about today, as we said in the introduction, is subcube quasi-randomness for Boolean functions. And this is a joint work with one of my advisors, Fan-Chung Graham, here at UCSD. So our motivating question in this area is sort of kind of an interplay between deterministic objects and random objects. And so I'll bring up the classical example of this, which is a quasi-random graph. The basic idea is, how do we quantify this notion that a particular deterministic graph looks like it was drawn uniformly at random from, say, the GNP model of random graphs? And in particular, what are some of these key properties that you can see in a random graph model like GNP? Now, of course, there is entire sections of this conference and others that are devoted to the various properties of GNP, but there are going to be a few in particular that we're going to focus on. One of them is that if I give you any fixed graph H, think of H as a triangle, and count the number of times in GNP that I have a copy of a triangle, it's going to be about n to the number of vertices of H times p to the number of edges. So one thing that we could do if I'm given a deterministic graph is count the number of copies of any fixed graph inside of this guy. Another property that I might want to look at is, if I pick a large set of vertices, how many edges live inside that set? And in GNP, this is about p times the size of the subset choose 2. And so this would be another thing that you could check in a random graph, or in a fixed graph, to see if it is quote unquote quasi-random. And a very similar but subtly different property would be to look at two different set of edges and two different set of vertices and count the number of edges that go between them. Now, you might notice none of these tests, if you will, are particularly easy. They involve checking a very, very large amount of information. And while we could conceivably, in principle, check them for a deterministic graph, what we'd really like here is a theorem that says some of these tests are actually equivalent to each other. That if I pass one test, I pass, say, all three of the ones that were just listed here. And thankfully, and the paper that really got this whole subject off the ground was a result by Chung, Graham, and Wilson from 1989, which states the following. If I give you a graph G on n vertices, where n is thought of as going to infinity, the following properties are all equivalent. First off, they're 1 plus little 1 copies of any particular subgraph H in this particular graph. Now, the important point to note here, and please ignore the little typo with the vertex set right there. The important point to note here is that the graph itself is deterministic. There's no randomness involved. We're literally just counting the number of copies of subgraphs. And this right here is somewhat amazing, that we can count, that we have this massive number of graphs that we'd be counting, and all of them have about the same counts as you would in GNP. So this is our first quasi-random property. The second, related to what I had on the previous slide, is that if I look at any large set of vertices, the number of edges in it is about what it should be in GNP. And similarly, if I look at two different sets of vertices, look at the edges going between them, it should also be the same as GNP. And I mentioned that all three of these are hard to test. Let me give you now a property that is equivalent to all of these, but is actually reasonable. If I count the number of induced 4 cycles in GNP, and it is close in my deterministic graph, and it is close to what you find in GNP, then all of these other properties also hold. Which is kind of insane when you think about it, because I have one graph, a 4-vertex graph. If I count the number of induced copies of it, if I give you any graph on 1,000 vertices, that if there are the appropriate number of force cycles, my 1000 vertex graph also fits in my deterministic graph about as many times as it would in GNP. So in other words, C4 really controls all of these things, all of these properties. And furthermore, it's actually a reasonable property to check. And this is something that I'd like for you guys to keep in mind for the remainder of the talk, because this is really the focus that I have taken on this particular part of the work, of finding some small object that controls the counts of an arbitrary object. And I'll also mention that ever since this 1989 paper, there has been a great deal of work on quasi-random properties for other combinatorial objects, in particular, K-uniform hypergraphs, subsets of the integers, permutations, and even certain subclasses of graphs and hypergraphs. In particular, as I mentioned, as my title mentions, my work is about doing this exact same idea, this exact same type of theorem, but for a different combinatorial object, namely Boolean functions. So in particular, the work that I'll be doing ahead for what I'll be presenting later, a Boolean function for us will be a map from f2 to the n to f2, where f2 is the finite vector, is the finite field with 2 elements. If another very valid way to think about this is just a map from binary strings to true and false. And from that perspective, we will also occasionally find it useful to think about this as a map from f2 to the n to plus minus 1, viewed as a subset of the complex numbers, where -1 is true, 1 is false. And just as an example of one of these functions, I'll present you guys the parity function, which counts is the number of ones in my input, even or odd. And over f2, that is the same thing as just adding up all the bits in my input and keeping, since addition over f2 keeps track of whether things are even or odd. And so these will be the central objects of study here. And in particular, my notion of a random function will be a uniformly random map from f2 to the n to f2, of which there are 2 to the 2 to the n of them. Now, these are actually quite nice objects. Because f2 to the n is finite, you can show that every Boolean function is not just a function, it is also a multilinear polynomial in the input bits, which is a hugely useful property and makes studying them much simpler. And to sort of see how you can derive that, let me give you a nice little example. I'm going to pick a particular Boolean function. It's going to be defined to be 1 if and only if my input is exactly all zeros. Now, what would this function do? Well, one way to write it down is that I take the product over all of my input bits of 1 plus the input bit viewed over f2. If any of my input bits xi are 1, 1 plus that will be 0, and the whole product will disappear. But if they're all 0, then I just get a product of ones. However, if I expand this thing out using binomial theorem and reduce mod 2, I'm going to get a massive sum over subsets of n, and then the product of all of the inputs in a particular set. And this construction actually generalizes to say that any Boolean function can be written as a multilinear polynomial in this fashion. And so from that, we actually get a well-defined notion of degree for a Boolean function. And keep that one in the back of your head for a little bit. I will be referring to it in just a bit later. Because the notion of quasi-randomness that I'd like to introduce for these functions is actually a little bit different. And to do so, I'll define something called a subcube. And it's a subcube of dimension d is basically just an affine subspace over f2 to the n, viewed as a vector space. Now, why will I have all this new notation for it? Why do I introduce a new name? The reason is that I'm not keeping track of the affine subspace. I actually want to keep track of not only the affine shift B, but also a specified basis, which I'll represent as a matrix M. And the other key part about this is that the dimension D only refers to the dimensions on M. It does not refer to the rank. So in particular, a subcube of dimension D might not actually have dimension D as an affine subspace. It is simply defined by a matrix that is n by d. And this is useful later on when we start talking about averaging over all of these. It makes the counting a lot simpler. And what's the upshot of all of these guys? Well, what I'm going to be looking at, much like we had with embeddings of subgraphs and graphs, I'm going to be embedding smaller functions in bigger ones. So in particular, I'll take a map H from F2 to the D, where D is thought of as constant, to F2, and embed it in a bigger function, F2 to the n to F2, by finding some subcube. And this is where we really do need the specified shift and basis, such that the following equation is true. That if I pick any input to H and use the definition of my subcube to get a vector in an affine subspace, the function H and the function F are exactly equal to each other for all points in my subspace, or in my subcube. And this will be our notion of subgraph or subpattern in permutation. This is the analogous count of sub-objects that we're going to want to turn into a quasi-random property. And just as an example to see how this works, if I pick the constant function on 2 bits that always returns the constant 1, and then I'll let my function f be the parity function, which I mentioned earlier, then I can pick the following subcube with 1, 0, 1, 1, 0, 1, and then a shift of 1, 0, 0 that will actually be a perfect embedding of the constant function into the parity function. And you can check this by simply plugging everything in and letting v1 and v2 be the input bits to h. And the way this ends up working is that the parity function actually divides the space into 2 large affine subspaces. This subcube that I have picked right here happens to be a subspace of one of those larger affine subspaces. And this more generally is the type of pattern that we're looking for, that if I pick just the right subcube, I'm going to get an actual embedding of a particular function into my big guy. So with this notion in hand, let me also define EM of HF to be the normalized number of embeddings of H in F, i.e. the count of all of the possible subcubes where H embeds in F divided by the total number of possible subcubes. And this is the first part where we actually use the fact that D is not necessarily the dimension of a subspace. This is simply the dimension of the matrix. It makes this count here at the bottom quite nice. And so putting all of these things together, we have the following result. That if I give you a fixed deterministic Boolean function, and I fix a d greater than or equal to 1 and let n go to infinity, then the following are equivalent. Any function that I want, any function on a constant on d bits, embeds about the same number of times as it would in expectation in a random function. The Gowers uniformity norm of f is small. I'll talk about that in just a little bit, seeing as I haven't defined it. And then 3, and this is the part I really want you guys to think about, is that instead of looking at all functions, if I embed constant functions on at most d bits in my Boolean function, and it occurs about the same number of times as it would randomly, then every function embeds about the same number of times as it would in a random function. The only subtlety here, and you may have noticed this in the first theorem, is that previously we just counted subgraphs, but C4s had to be induced C4s. There's a similar parallel here, wherein any function can appear, but we only count the ones on exactly d bits. For constant functions, we actually need the property to hold. We need to have about the number of constant functions as in a random function for every value 1 up through d. So we need to have a much tighter concentration all the way up to level d as compared to our first one. So to give a little sketch of how we might prove this, the first implication 1 to 2 is actually quite simple. Basically, once you write down the definitions of the Gowers norm and the definition of embeddings, it just goes through. The implication from the Gowers norm to embedding of constant functions uses the well-known Cauchy-Schwarz-Gowers inequality and is relatively simple once you've digested that particular statement. The heart of the proof is going from constant functions back to all functions. And roughly speaking, the way it works is we induct on D and then extend various embeddings that we already have to larger embeddings. And the key property is that these extensions can be symmetrized. Essentially, I can forget about which function in particular I am embedding and only look at a very, very uniform object. And this is where the constant functions come in. And so to finally finish things off, I do want to mention a bit about the Gowers norms. Rather than define them, I'll simply state these are known to control correlation with degree D polynomials. So in some sense, you can think of this theorem as stating that these functions that I am discussing, these quasi-random functions, are far from degree D polynomials. And in fact, there are two other properties that you can join on almost immediately after that. They're a bit more technical to define, which is why I haven't gone through them. And furthermore, we actually do have explicit bounds for all but one of the connections in these equivalences. And this is something that we plan to be looking at in the future. And so with that, I think I will stop here. And thank you for listening.
All right, let's go ahead and thank the speaker. You may unmute yourselves and applaud or use the clap react within Zoom itself. All right, so at this point, we will take any questions that you may have for Nicholas. Feel free to type them in the chat or unmute yourself and ask. Okay, so let me pose a question for you, Nicholas. So when you talked about the notion of a discrete embedding, myself predominantly being an analyst, my mind jumps to something a little different. Is your definition of discrete embedding, in some sense, an analog of, say, a continuous embedding, say, between LP spaces?
This is a good question. And I think here, you could possibly massage the definition into something like that.
Okay.
I'll say that the focus is very different. And the reason being that D here is typically thought of as a constant. So if I'm looking at the embeddings as I've defined them here, I'm picking subspaces of dimension at most D inside my space, and then checking, is the function exactly equal to it on that space?
Yes, that's very different from what I
it could be massaged. If you really wanted to, I'm certain you could look at like an up to measure 0 version of this, where we have like almost everywhere equality or something like that, and start looking at an infinitary version, which there is a lot of work in the quasi-randomness regarding infinitary versions of this. So yeah, very interesting question.
Thanks. So anyone else want to ask a question? All right, I suppose not. Let's go ahead and thank our speaker once more, and we will get ready for our second talk, which should begin in about a minute.
Thank you.